right, team. Good morning to you. You ready for video number 8 for our acids and base journey for my class S chapter 16, of course. So we're over halfway through with this baby. Again, long chapters for second semester general chemistry, because there's a lot of review I like to touch up on and application of that to some new concepts, or we open a bigger ugly door that we've refused to open in some of the earlier intro classes. Sometimes we don't say stuff in the earlier classes because it's not really necessary at the time. So we don't get everybody to drop on us. Right? Sometimes we make some generalizations, but we get to open the big ugly door a little bit more in this second semester of general chemistry. All right, we've been looking at solutions of strong acids and strong bases. We've covered solutions of weak acids and weak bases. What we're going to do now is similar, but not so intuitively obvious, I don't think. A lot, because we've been looking at acids as something that has a hydrogen ion to donate, right? Bases typically as amines, derivatives of ammonia. But some things aren't so obvious, particularly ions. So what we're going to focus on this video is the pH of salt solutions. And remember, a salt is just a generic term a chemist uses for an ionic compound. And we're going to focus specifically on soluble ionic compounds. If you review your solubility table, you'll see that there's a lot of 100% soluble salts. And we consider those strong electrolytes. So review that solubility table. And any strong electrolyte, any soluble ionic compound, we're going to make the assumption that it dissolves 100% when placed in water to make a salt solution, right? Which will contain a cation anion. For example, if you remember from prior classes, if we had sodium sulfate, we know that sodium salts are always 100% soluble, so that's considered a strong electrolyte. So that will dissociate or break apart 100% to give us 2 sodium ions, right? So the subscript there becomes the coefficient there, maintain balance, and then 1 sulfate ion in that particular example. So a sodium sulfate solution is going to contain some sodium ions and some sulfate ions in there. Those may have acidic or basic character. Not as intuitively obvious, but we'll show you how to do that in this video. A lot of times you'll hear people call this process hydrolysis, the breaking apart of something by water molecules. Those water molecules come in and rip those ions apart. The partial negative side of water on the oxygen is attracted to the cations. The partial positive side, where the hydrogens are on water, is attracted to the anions over there. You can review that process from prior classes if you need to. But we tend to like to use dissociate, so we use the dissociation equation to represent that. You don't ever have to show this dissociation equation. A lot of you can just do that in your head and go, okay, this is my cation, this is my anion, and the focus of this video is to go, does that cation or does that anion have any kind of acidic or basic behavior, right? So if it had basic behavior, it'd be able to extract a proton from water, take an H plus from water, producing OH minus, and giving it a pH greater than 7. Well, may not be so obvious, but maybe that ion has a hydrogen it could donate, right? An acidic hydrogen, which could form H3O plus. Let's take a look at some things. If you need to, get out your polyatomic ion handout. You find out wherever it is, but for my class, you can download that from my Canvas site. You hopefully have a hard copy of that already or have it on your phone. So study that. The better you know your polyatomic ions, the better. So here's another problem we could look at. A little more complicated than this one. So we've got ammonium oxalate. And from your solubility, ammonium ions are always soluble, right? If we have an insoluble solid, we're going to treat that in chapter 18. So that's not going to count for this one. So if I have ammonium oxalate, that's going to dissociate or undergo hydrolysis 100%, giving us 2. See the subscript there? That comes over, gives us 2 ammonium ions. And we'll also get the oxalate anion. So if you don't recognize the oxalate anion, you need to study your polyatomic ions, my friend. All right. So let's, I'm going to pause this and erase the board, and then we'll take a look at how do you recognize whether a cation or an anion has acidic or basic behavior. And if it does, well, we might have to do ice tables like we did before. Sweet. All right, guys, we're going to look at 5 different categories of ions. I think your textbook breaks them up into 4, but I'm going to break it up into 5 just to specify things. So what the textbook does is it takes these and puts numbers 1 and 2 into one category. The first category I'm going to look at are cations from strong bases, right? If you remember strong bases, at least in my class, we're looking at alkaline metal hydroxides and many of the alkaline earth metal hydroxides as well. For example, sodium hydroxide, potassium hydroxide are your prototypical strong bases. And again, those just dissociate. They're ionic compounds. They just dissociate in water 100%, forming the cation, the Na plus, the K plus, whatever it is, and the anion, the OH minus. Of course, the OH minus is your strong base there. But we're specifically looking at these cations, right? Well, does that have acidic or basic behavior? Turns out that these cations are neutral, right? And I'm going to mention why in a second. And then in the same way of looking at it, anions from strong acids, which are their conjugate bases. So if you remember, let's grab an acid-base table real quick. And let's look at those. You should, again, have those strong acids memorized. But again, if you look at your acid-base table here, and you can look at any acid-base table. This is the one from your general chemistry notebook, right? The strongest acids are up on top, and their conjugate base is next to it, right? And the stronger the acid, the weaker its conjugate base. So very strong acids here have such weak conjugate bases, they don't even ionize in water, right? So they cannot react with water. They're above water. See the water here? They're above water, so they don't react with water. They're too wimpy, right? And the weaker the acid, the stronger its conjugate base, until you get all the way down here. These ones have really, really strong conjugate bases. These weak acids here, they will have conjugate bases stronger than water. They're below water, so they'll be able to ionize in water and react with it. So these ions right here are not going to be able to function as bases in solution. So I wrote those on there. So these are the conjugate bases of the main strong acids that we'll be dealing with. We're not going to really deal with organic strong bases. That's a little more than we like to deal with. These are neutral. So the general concept is any ions, conjugates, any conjugate species from the strong acid or strong base is so weak because it's coming from a strong species. The conjugate's so weak, it cannot react or ionize with water. It's too wimpy, so they are neutral. And a general way to think about it, the stronger the acid or base, the weaker its conjugate species is. They're opposites on the acid-base table, right? As you move from the strong acids on top, who have very weak conjugate bases, as the acids get stronger, the conjugate bases get as the acids are stronger, the weaker the conjugate base, and as the acids get weaker as you go down the table, the conjugate bases get stronger and stronger. So it's good to study that acid-base table a little bit. Let's look at it. So these are pretty simple. So anytime you see sodium, potassium, any of those alkaline metals, or any of these anions, those are going to be neutral. We don't have to worry about acidic or basic behavior. Now let's look at the conjugate species from weak acids and weak bases. That's a whole different scenario because their conjugates will be strong enough to ionize in water. All right, let's take a look at some of the next types of ions you're going to run into. You're either going to run in cations from strong bases, anions from strong acids, right? Or the conjugate acids of weak bases or the conjugate bases of weak acids, right? So if I take, for example, a weak base and it ionizes in water, it's going to produce its conjugate acid, which is most commonly a cation. So we'll say cations from weak bases. If you look on your acid-base table, if I look at my weak bases, right? So these are so here's my bases right here, weaker bases on top, right? They get stronger and stronger and stronger until you get to the bottom, and we got our very strong bases down here. So if I take a weak base, right, any of these weak bases right here, its conjugate acid is over here, right? So once it reacts, it's going to form its conjugate acid. These conjugate acids right here, right, they're above water. See where water is right here? So any acid above water, since acids are stronger on top, Any acid above water is a stronger acid than water, so it will react with water as an acid. So any weak base, right, that produces a conjugate acid higher than water, that's going to ionize in water and create an acidic solution. It'll be a weak acid, so we could apply ice table problems to that. So for example, here's some very common weak bases: ammonia, methylamine. These are pretty common weak bases, or anything on that acid base table that you can see. There's a whole bunch of them that you wouldn't think about. Well, if that reacts, it picks up an H plus. So remember to review conjugate acid base pairs, or a base conjugate acid and acid conjugate base pairs. You got to think about what it becomes when the base gains an H plus or the acid loses an H plus. So if ammonia gains an H plus, that's its conjugate acid. If methylamine gains an H plus, it forms the methylammonium ion. These, if I bring those down, are stronger than water. So they'll react with water by donating the H plus, right? They're more acidic than water. You can actually do the ionization equation for that. Where'd my blue pen go? Here it is. So if this loses its H plus, it becomes CH3, NH2, and then this becomes H3O plus. So we get the hydronium ion. So the conjugate acids from weak bases will ionize in water, producing the hydronium ion. And that's why they are weakly acidic solutions. Oh, getting kind of weird. So it's nice to have that acid base table with you and a list of Ka and Kb values. And if you can't find the Ka or Kb value, you can look back in one of the other videos where I show you how to determine that with Kw equals Ka times Kb. All right, let's look at the next category. Just like the cations from weak bases, what if I have anions from weak acids? So in this case, that would be its conjugate base. When a weak acid ionizes in water, it produces the hydronium ion and its conjugate base. Well, is that conjugate base stronger than water? That's the question. If it is, it's going to react with water. If it isn't, it's going to be neutral. And remember, the stronger the acid, the weaker its conjugate. The stronger the base, the weaker its conjugate. So weak acids will produce conjugate bases that function as weak bases. They're stronger than water. And if we look at this table again, let's look at our weak acids here. So acids are strongest on top. So these will produce neutral ions. They're weaker than water, right? And any of these weak acids that are below the hydronium ion here, any of these will produce conjugate bases that are stronger than water, right? In the base column, they're stronger going down. So any of these bases below water will ionize in water. So any acid producing a conjugate base that's below that water will be strong enough to react with water and ionize and produce some OH minus. For example, if I have these weak acids, right, hydrofluoric acid, nitrous acid, the hydrogen carbonate ion actually functions as a weak acid if you look on the acid base table. Any of those, after they lose their H plus, will produce this. So HF becomes the conjugate base, the fluoride ion. The bicarbonate ion becomes the carbonate ion. Nitrous acid becomes the nitrite ion. So these are their conjugate bases. These are stronger than water on the acid base table, so they will react with water, and they will form weakly basic solutions with pHs greater than 7. Whoa! And we can do ice tables with that. So do this equation for me. Pause the video, and let's say I have the nitrite ion, right, which is the conjugate base of a weak acid. Therefore, it's slightly basic in water. That is going to function as a base, so that is going to take an H plus from water. Figure out what you get. So this will become HNO2, and then the water loses a proton and becomes hydroxide. And since it produces hydroxide ions, it's going to be weakly basic and produce a pH greater than 7, less than 14, and we can do ice tables with that. All right, one more classification of ions, the most complicated one, and then we can do some ice tables with these. All right, gang, to end off this video on the introduction to ions as acids and bases, It gets a little tricky if you have a salt that has a cation that's weakly acidic and an anion that's weakly basic. It's kind of like they counteract each other. You're like, oh my gosh. So salts that produce acidic cations and basic anions. Oh man, what are we going to do? All the other ones we talked about only produce one ion that has acidic or basic behavior. The other one's neutral. What we're going to do is we're going to analyze that soluble salt, think about or write down the dissociation equation and go, what is the cation that's produced? We'll do an example in a second. I'm just giving you an overview right now. So what's the cation produced and what's the anion produced? All right. Look at the cation. What's its acidity? If it's weak, which it will be, we're going to look up its Ka value. Look at the anion. Look at its ability to act as a weak base. Look up its Kb value. Again, you can usually, if it's on the Ka-Kb table, great. If it's not, use that trick we had before where Kw equals Ka times Kb. If the Ka value of the weak acid ion is greater than the Kb value of the weak base ion, the overall solution will have acidic character to it, a pH less than 7. If the Kb value of the weakly basic ion is greater than the Ka value of the weakly acidic ion, then the overall solution will have a basic character to it. I won't give you these problems as far as ice tables and stuff on exams, but I could certainly do what I'm going to do next, where I give you a salt and say, what is the cation, what's the anion? Will this have an overall acidic or basic character, or even neutral character? But I'm not going to have you do the ice table with that where you have competing aspects of it. The ones I'll give you on quizzes and exams will just have one ion, either the cation or anion acts as an acid or base, and you can do ice tables with that. Did you notice my shirt today? As I come closer, it's a blue shift. As I get further away, it's a red shift for my physics fans out there. All right, let's do an example real quick. I don't know where I get all these dumb shirts. All right, here we go. See if you can do this ahead of me. So you can pause this video, write this problem down, and then take a look at your acid-base tables and see, first write the dissociation equation. So we've got a salt solution of ammonium fluoride, NH4F. Is that acidic, basic, or neutral? So either do it in your head, or write down the dissociation equation, or some people call it the hydrolysis process, and show me what the cation is and what the anion is with its charge, right? Then look on your acid-base tables and see if those would function as weak acids or weak bases, or would they be neutral? And if they are acidic or basic, look up their Ka values for the weak acid ion and look up the Kb value for the weak base. And compare those. If Ka is bigger than Kb, it'll be an acidic solution. If Kb is bigger than Ka, it'll be acidic solution. And if Ka equals Kb, that's probably not going to happen. Exceedingly rare. Then you'd have a neutral solution. All right, so give it a shot. While you're doing that, I will write these up on the board. Let me do the dissociation equation. So ammonium fluoride, right? Once it dissolves, it's an ammonium one, so it's 100% soluble, so this is a strong electrolyte. So to 100% extent, that's going to break up into the cation, the ammonium ion, and the anion is the fluoride ion. You don't have to write that, but I find it helps me identify what things are when I'm looking for them. I tend to lose track. If I got too much going into my head, I lose track of things. Just ask my wife on that one, right? It's like just give me 2 or 3 things to go get at the store. Once it's 4 or 5, I can't remember them, and I need a list, right? But 2 or 3 things I can handle. So I have a habit of writing things down because when I'm focusing on the next step, I forgot the first step. Simple mind. But if I could get a PhD, you can get an A in my class. I say this almost every day to you guys, especially when you watch me lecture. You're like, yeah, if this dude can get a PhD, I can certainly get an A in this class. I had focus issues when I was a student, but it was just hard. How bad do you want it, baby? If you want it bad enough, you can overcome all the obstacles that are in your way. It doesn't matter. Your mind can overcome anything that life throws at you if you try hard enough. I just didn't sleep a whole lot because I had to study like 3 times harder than everybody else because I couldn't focus very well, as you're finding out on my lectures. Although these videos allow me to focus a lot more than my live lectures. If you guys remember my live lectures, I go down bunny trails all the time and crazy tangents and weird stories, but we'd always come back home, wouldn't we? So I can focus a little bit more on these lectures, so we're a little more efficient, but we're having fun. At least I'm having fun. All right, let's take a look at our 2 species here. Let's bring the ammonium ion down. Now, the ammonium ion is the conjugate acid of a weak base. That comes from NH3. So let's take a look. If you look at under the acids, let's see if we can find NH4+. Do you see NH4+ right there? Right? That's the conjugate acid of ammonia. Right? Boop. So NH4+ is higher than water. Right? Remember, acids are stronger at the top and get weaker as they go down. So anything above water is going to be a strong enough acid to react with water. So the ammonium ion is weakly acidic. It's going to react with water. So let's do that. Let's do the ionization equation. That's going to function. This is my weak acid. It is an ion that's weakly acidic. It's going to donate its H+ over to water, giving us ammonia, the conjugate base there, and then the water becomes the hydronium ion. Let's look up the Ka value for that. Now, on my acid-base table, I don't have K values on here, right? Darn, man, I need another paper. So we'll go over and find our Ka table, which you by now should have printed out, I would hope. So here's my Ka values. Let's look up ammonia. So let's see, do we see ammonia on there? Ammonia. No, this isn't good. I don't see ammonia anywhere. You see ammonia anywhere? No ammonia. Oh no, ammonium ion. I don't see the ammonium ion anywhere. Oh no. And you're on the test and you go, oh crap, it's an oh crap moment. What do I do? We're going to have to figure it out. Okay, so we'll do that in a second. Let's write up the other equation and look for that value, and then we'll calculate the Ka value for this because it's not on the table. Oh no! Here we go. Let's take a look at the fluoride ion. Let's bring that baby down. Actually, I'm going to move that a little bit lower. Yep. Let's look at the fluoride ion. Let's see if that has some basic character, because that comes from HF, right? That's the conjugate base of hydrofluoric acid, which is a weak acid. So conjugate bases of weak acids are basic. So let's take a look at our acid-base table. All right, so let's take a look. So there's HF, right? So it produces its conjugate base, F-, which is below water. So that is a stronger base. The fluoride ion is below water. So the fluoride ion is strong enough to ionize in water. So let's do that equation. And that's weak. So this is my weak base. That's going to take an H+ from water. And we're going to get HF, and then that loses an H+, forming OH-. So you see the acidic character of that one and the basic character of this one. So we need the Ka of this, and we need the Kb of this. And if I look on the Kb's, where's my Kb's? If you look on there, there's no fluoride ion. No! Oh, man. All right. So we're going to have to calculate the Ka and Kb values for these babies. I want you to pause this and go review the video that allows us to calculate the Ka and Kb values for things that are not on the table. So remember, Kw equals Ka times Kb. So take a second to go do that. All right, did you do it, gang? So I took some time to erase the board so we had a little bit more room to do these calculations. They're not hard calculations, just a simple algebraic equation, but you're going to do it quite a bit for these kinds of problems. All right, so we're looking for the Ka value for the ammonium ion and the Kb value for the fluoride ion. So let's rearrange this. So I want the Ka value for ammonium. That will be equal to Kw divided by Kb. Now, this is where most students screw up. They do the wrong value of Kb for some particular reason. You want to do the Kb value of its conjugate base. So the conjugate base of this, so the ammonium is the conjugate base of the ammonium ion. That's the Kb value that you put in there, right? So it's the Kb value of the conjugate base that it forms. So we know Kw. I'll provide that for you on exams. That's 1.0 times 10 to the minus 14th. Sometimes you'll see that again as 1.00. Not a big deal. The Kb for ammonia. Now remember, the ammonium ion we couldn't find, but I can find ammonia. So let's look on our Kb table here. You see ammonia. It's the very first one. Do you see the 1.8 times 10 to the minus 5? So let's plug in 1.8 times 10 to the minus 5. So we're going to get two significant digits here. Pop that in your calculator, and you'll get a 5.5 forever in your calculator. So just give me the two significant digits with a vertical dash line. Give me two non-significant digits past it. You can do more, but they're not necessary. Times 10 to the minus 10. And if we rounded that, we would get 5.6 times 10 to the minus 10. So that's the Ka for the ammonium ion. So again, that's how you figure out Ka values for something that's not on the Ka table. Yay! Very easy to do. Now pause this and do the same thing for the fluoride ion. We're looking for the Kb value for the fluoride ion, which we couldn't find on the Kb table. Do exactly the same thing. So pause it, see if you get what I get. I'll go ahead and work through it. So Kb for the fluoride ion will be equal to Kw, that constant, divided by Ka of its conjugate acid. So that's going to be the Ka of the hydrofluoric acid. So Kw, which you probably have memorized by now, right? That's for the auto-ionization of water. Let's look up the Ka value for HF. So let me grab my Ka table. Let's look up hydrofluoric acid. So let's look up H for hydro. Looks like it's right there. Hydrofluoric acid. It's in alphabetical order. There's my HF. Looks like it has a Ka value of 6.6 times 10 to the minus 4. Everybody got that right there? 6.6. So hydrofluoric acid, HF, 6.6 times 10 to the minus 4, baby. 6.6 times 10 minus 4. Two significant figures all around, and I get 1.515. Good to two significant digits. Right, put that vertical dashed line times 10 to the minus 11th. So that does not round up, so it'll be 1.5 times 10 to the minus 11th equals our Kb. Rocking and rolling. Now all we got to do is compare the Ka. Where'd my red pen go? It's over here. Let's compare the Ka for the ammonium ion versus the Kb from the fluoride ion. Because remember, we're looking at this salt solution of ammonium fluoride. Which is bigger? Well, the Ka is slightly bigger than the Kb, which means this will be a slightly acidic solution. So we can say Ka is slightly bigger than Kb. So this will be a slightly acidic solution. I don't know what the pH will be. I know it'll be a little bit less than 7 probably, but I do know that this particular salt, which actually has a conjugate acid and conjugate base, that part of it, those ions are, so they'll ionize in water and compete against each other, but the acid's going to win just a little bit. So that's it for this video. We're going to do a shorter one next and look at another salt solution, but we're going to actually calculate the pH of the salt solution.